Climate change is an issue in desperate need of a solution, and until a fully viable replacement is found for fossil fuels, the use of current renewable energy sources needs to be refined and enhanced as much as possible. One of the most easily utilizable forms of natural energy is the wind. It has been used to power ships for several millennia, and has been used to generate electricity for more than a century. The most common and easily recognizable wind turbines have an output of 1.5 megawatts, which can each provide enough energy to power several hundred average homes. Since the wind is free to acquire, the only costs associated with a wind turbine are installation and maintenance. The biggest benefit of wind turbines, however, is their carbon footprint. Nothing, meaning they are a clean source of renewable energy. Our project was about maximizing the power output of a turbine from a given set of constraints.
Our first consideration was to go with the two-blade design, which folded thanks to a hinge mechanism to aim for a larger blade design within the size constraint. It is worth noting that a three-blade design was not considered, as yawing was not a consideration, and a one-blade design would need a large counterweight due to the material constraint. A single airfoil along the blade was also chosen, as switching airfoils midspan often results in distorted and bumpy surfaces. Lastly, we chose to have minimum chord taper at the root due to maximum stresses occurring at the root. The turbine had to have a horizontal axis design, with a clockwise rotation and a maximum angular velocity less than 3000 rpm. In addition, it had to have a tip speed ratio between 3 and 8, as well as being a 3D printed as one single part and able to fit in the following box with a length of 400 mm, depth of 100 and height of 150 mm. In addition, a mass limit of 200 grams has been imposed. Our objective was to maximize the power coefficient of the turbine, defined as the ratio of the power delivered to the turbine to the total power available in the flow passing through the swept area of the blades at a stated design TSR of 5.5. Our requirements when choosing the airfoil were firstly to have a lift-to-drag ratio which was high, with a thin airfoil profile, and a coefficient of drag that was low. In addition, we needed an airfoil which was optimized for a Reynolds number of 100,000, and we had to incorporate twist to maintain an optimal angle of attack. The SG6043 and 818 airfoils were shortlisted due to the high lift-to-drag ratio. Although the A18 had a higher lift-to-drag ratio, its thin profile and sudden peak in stall would affect structural and off-design performance. The SG6043 airfoil was selected as this airfoil has been optimized for low Reynolds flows and experiences a plateau region around the stall, imposing a safety margin during testing. To calculate the variation of twist and chord along the blade, the Betz and Schmitz formula were implemented in a MATLAB code. The input variables were TSR, wind speed, number of blades, CL max, CD, density, and blade radius to output the individual sectional twist and chord lengths. One of the limitations in the Betz model was the fact that the induced rotation in the wake due to the rotating blades was not considered. Finally, the Schmitz model was implemented as both axial and tangential induction factors were considered, as well as providing a greater structural integrity.
Horner wingtips were used to maximize the effective wingspan of the blade without increasing the geometric wingspan.
The similarity between operating conditions seen by the Swift and the wind turbine implied a comparable Reynolds number experienced in both cases. This encouraged us to incorporate a back sweep to our blade as seen in the Swift. It was found that up to an 8 degrees backward sweep can increase the efficiency of the wind turbine. This increase in efficiency is due to the positive radial pressure gradient. It was found that the shape of the nose cone did not have large impact on the overall aerodynamic performance of the blades, especially at low speeds. Hence, a simple parabolic streamlined cone was designed with the purpose of minimizing drag. A simple hinge was designed to be able to fit our blade into the printing box. The main consideration of this hinge was its placement on the turbine. To avoid interferences and consequently turbulent flow on the wing, the hinge was decided to be placed behind the nose cone.
To ensure that our turbine blade will not fail during testing and operation, a detailed structural analysis was required. Using the blade sections that were split earlier, we first calculated the stress due to centrifugal force along the blade section. We first calculated the force at a certain section of the blade, and then, to get the centrifugal force at a specific radius of the blade, the force is summed towards the root of the blade. Next, we had to calculate the bending moments along the blade. For the moments along the blade was first modeled into a cantilever beam, and the bending moments were then calculated on MATLAB. The second moment of area of the blade was also estimated for every section of the blade using parameters of the proportionality coefficient, chord, thickness ratio, and camber ratio. Along with the bending moments, this was used to calculate the stresses acting along the blade. The component of stresses at the wind direction and blade velocity direction was then added with the stresses due to centrifugal force to get an overall direct stress acting on the blade section. It is observed that along the blade, the stresses were highest at the center of the blade section. The bending moments of the blade root had to be calculated separately as it had minimal aerodynamic effects on it. The stress occurring at the blade root was found to be 19 megapascals, which was well within the critical stress of the ABS plastic material. Another consideration we had to ensure was that the tip deflection was well within the necessary constraints for it to operate at its optimal performance. The max deflection was calculated using virtual work method. We found that the max deflection was approximately 8 mm. Other than neglecting shear stresses, some of the additional assumptions was that we neglected self-weight loading, neglected relatively small twists of the blade cross-section, and that we assumed bending moments are aligned with principal axes of the blade structural cross-section.
The entire manufacturing process of the designed turbine can be roughly split into 3 phases. First off, the hexagonal aluminium hub, which the turbine is mounted on, was produced in the workshop. The hub was first trimmed and smoothed out by the computer numerical controlled CNC lathe machine to achieve the design dimensions, and a hole was drilled in the middle. It was then cut into the desired hexagonal shape by the CNC milling machine. The hub was parted off from the rest of the material and engraved with our group number. Finally, a QA birch machine connected to a hydraulic press was used to finish off the hub manually. The second part of the process was the 3D printing of the blades. As the 2 blades were folded and connected by hinges, we first test printed the hinges to ensure that they will work. The group designed the trailing edge in the CAD software to an infinite point, so a thin layer of extra material was added to ensure successful printing. The last part was to sand off the extra material added to the trailing edge of the blades and to smooth out the surface using sandpapers. Finally, a thin layer of acetone was applied to the surface to ensure the smoothness, which will reduce skin friction and drag in the test.
To measure the performance of the wind turbine, it is first mounted on the testing rig in the section of the wind tunnel. The tunnel is then adjusted to the planned wind speed, and the turbine spins freely until its maximum preset RPM is reached. A controlled brake is then applied to the turbine, causing it to decelerate, and the torque and RPM are measured. When the turbine is slowed to the minimum preset RPM value, it is then accelerated by reducing the resistive force. This is repeated at wind speeds of 6, 8, 10 and 12 meters per second, and the power coefficient is determined for each. We found the maximum power to be 51.6 watts and its maximum power coefficient 0.235. There is a 12% difference between our experimental value of TSR at maximum CP and our theoretical prediction. It is difficult to say exactly why this is the case, as there are so many variables that could affect it. One possible explanation could be during the design process, we designed the blade to operate at maximum CL at the designed TSR. However, because the lift is proportional to the square of the velocity, it is possible that at a lower CL but at a higher rotational velocity, we could produce more lift, meaning more power at a higher TSR. There are several areas where we could improve if we were to do it again. Firstly, the turbine was only 145 grams, 55 grams inside the weight limit. This is far too conservative, and by designing the turbine to be closer to the 200 gram weight limit, the blades could have been made longer in order to increase the power it produces. The blades could have also been more tapered. This would have reduced the drag of the turbine considerably. Instead, we erred on the side of caution and chose to have less taper, to make the roots stronger so there was less chance of failure. The cone could have also been made using a honeycomb printing method, again saving weight, which have allowed us to make larger turbine blades.